Yeah. Well, it used to be, back when I was a student at La Sierra, Loma Linda, we took advanced statistics field trips, we called them, where you'd go out and eat $2 buffets and stay up all night. Okay, that, by the way, is inappropriate, and that's the beginning of our recording. Yay! Okay, so we're going to talk about Newton's laws. We'll finish up talking a little bit more about trajectories. First, a review of the entire homework assignment, because the scores weren't as high as I would hoped, and a lot of them were people who made small mistakes. So I figured I would just go over these real quick so you can see what you may or may not have done and why you did or didn't get credit. So the first problem was the tortoise and the hare. The tortoise goes slow and steady. The hare goes fast, slow, fast, slow. And the first question was, which one had the higher average speed? Well, the equation for average speed is the distance traveled divided by the time it took. If they run the same race, how do their distance traveled compare? Same. So then the only thing that can change is the time. And to get the highest V average, we simply need to have the shortest time. And so which one has the shortest time? The tortoise. So the tortoise had the highest average speed. Oops. About half the people said the hare, and there were varying reasons. So I want to make sure people understand why it's the tortoise that had the highest average speed. Everybody knew that the hare had the highest instantaneous speeds because it said he goes very fast. Second one, crumpled versus flat paper. The problem specifically said in an evacuated chamber. What does it mean if the chamber is evacuated? No air. At least half the students invoked air. And their answer would have been correct if there was air in the chamber. That is, the air would have slowed the descent of the flat one more than the crumpled one. But the problem specified an evacuated chamber. In an evacuated chamber, where there's no air resistance, how do the fall times compare? They're the same. And the reason why, at least one person had the reason why incorrect. Why do they fall at the same rate if there's no air? Constant acceleration of gravity. It doesn't matter which one has more mass, or in Aristotle's view, more earth. It only matters that you have the force of gravity pulling them down with the same acceleration. Okay, the next one, car accelerating from rest to 3 meters per second squared. Most people got pretty close on this. There was at least a third of you who forgot to make the plots. Now, I caught a couple people and they took them back and made the plots, but others, I didn't have a chance to send you back, and so not having the plots was a little damaging to the grade. You calculated, of course, the speed just by speed is equal to acceleration multiplied by time plus the initial speed, which is 0. And so you just had 0, 3, 6, 9, 12, 15, which made a nice straight line. Then for the distance is v initial t plus 1/2 at squared. So there you had, 1.5, 6, I don't remember, 13.5, 24, and 37.5. That's what they were. And those should have made a parabolic curve. There were a couple people who had straight-looking lines. One of them put numbers that were not linear on the vertical axis to make a straight line. It should have had a linear axis with a curve on it. This one here, I think there are 2 people who just straight up skipped it. Yeah, that's disappointing because you missed those points. It was just asking for the change in velocity from the first to the 4th second. So change in velocity, better use a vector sign. The velocity at 4 seconds minus the velocity at 1 second. A lot of people calculated that the speed at 4 seconds is 40 meters per second, and speed at 1 second was 10 meters per second, and just left it at that. But you were supposed to find the change in speed And actually not the change in speed, but the change in velocity. What's the difference in speed and velocity? Velocity has direction. So you need a direction in your answer. And I don't think there was a single person who put direction in their answer. And so the answer should have been 40 meters per second down minus 10 meters per second down equals 30 meters per second down. And like I said, there were some people who had the 30 meters per second, but no one that had the down. And then the final one, acceleration versus time graph. The graph looked like this. And virtually everyone calculated the average velocity, or excuse me, the average, not average at all, the acceleration. The acceleration correctly. That is, the acceleration is change in this case, speed over change in time. And so you had for the first one, 4 meters per second minus 0 divided by 4 seconds minus 0 is 1 meter per second squared. For the second one, 12 meters per second minus 4 meters per second divided by 8 seconds minus 4 seconds was 2 meters per second squared. There were some people who had the units wrong there. And then the average would be the total distance, 12 meters per second minus 0, or not distance, but speed difference, 12 meters per second minus 0, divided by 8 minus 0 is 1.5 meters per second squared. Part D asked you to compare the average for the trip with the average of the two numbers. In this case, those averages were the same. Why were they the same in this case? They weren't the same in the example we did in class, so why were they the same this time? It's actually a little bit of a flaw to have a problem which gives you a problem a lot of people make without an explanation. They were the same because it was the same time interval for both pieces. If the time intervals were different, the average between the two speeds would not be the same as the average speed. So any questions about that homework? I should get it posted as soon as class is over. I was working on that before class and then had to come teach. But they're all graded. Okay, then let's move forward. So projectile motion is what we've been talking about. I'm not going to read anything from this slide. Just a reminder, we've been talking about projectile motion, and that when you have something flying through the air like the ball, see if I can hit Denver from here. Shorty, wasn't it? Well, either that or Denver can't catch, but I think it was short. So when I threw the ball, it made a nice smooth arc. And what do we call its path? The trajectory. And as it was moving, how was it accelerating? Only in the vertical direction. It was accelerating downward. Why? Because gravity is in the vertical direction. So its horizontal component, its speed moving horizontally, what was that doing as it traveled from me to Denver? Assuming no air, of course. Constant, because the acceleration is vertical. So if you solve a problem with the trajectory, you just take the vertical motion completely separate from the horizontal, and you use the same equations we've been using, just one for vertical, one for horizontal. Now, have you guys all seen Speed? Okay, I'm going to show a little clip from Speed here with physics overlay, and of course, I can't do it without having the physics. And I believe I have to reload it because...
In the movie Speed, a bus is forced to jump an unfinished portion of the highway to avoid setting off a bomb on the bus. This bomb is rigged to explode if the bus goes below 50 miles an hour. Of course, they make it, but we want to know if this could really happen. First, it's important to understand how projectiles fly through the air. All objects, regardless of their mass, fall at the same rate in a vacuum.
Well, in my left hand I have a feather. In my right hand a hammer. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that?
Additionally, an object's time falling is independent of its horizontal velocity. So no matter how fast the bus is traveling, should it launch horizontally, it will always fall some amount and fail to make it. So, for the bus to make the jump, it must launch at some angle. Now this is a little bit of a cheat, as I should explain more. However, there is an equation in mechanics known as the range equation, which relates the initial velocity of a projectile to the distance it covers horizontally. If we examine the movie, we can find the speed the bus is traveling and the distance it is meant to cover. G is the acceleration due to gravity, which we know. So we can check to see how much of an incline we need to launch something that will just make it. We simply rearrange the equation, solving for the launch angle, plug in our values, and presto, we get approximately 5 degrees. That's not much of an angle. Now, there's no clear shot of a highway, so it's hard to say if there's actually an incline. But it seems possible there could be. Oddly, the bus seems to jump upward at the last moment, an artifact of Hollywood tinkering. But it does seem to be cleared one hurdle. If we really believe the bus left the road going 68 miles an hour, and the jump adjusted to the length of the bus was a mere 50 feet, as long as there was a 5-degree incline, it seems possible the bus could have made the jump. However, a quick glimpse at the Speed DVD's special features makes it clear the landing would most likely wreck the bus, not to mention we haven't thought about wind resistance or the bus's rotation.
If you road trip, did that right?
It's not entirely absurd.
It is entirely absurd, and here's why. You can argue this in a pure logical sense. Actually, I wanted to stay on this. You can argue in a pure logical sense. You're driving down the road. If you could jump that, that means that when the road is complete and you drive over that section, you're still going to leave the road when you're driving over that section. You're going to be doing a little hover action above the road. How many people believe our freeways are designed so you hover? Yeah, the overpasses don't have you taking it off and landing again. So there's no way that it would have been built to have enough of an angle to throw you off of the road. So it couldn't really happen, but for Hollywood, and you can watch the production, they show you all the jumps they put up there, the ramps to make it jump. And it's fun, use of the physics. You saw there, Denford, the range equation. That equation is only correct if you start and end at the same elevations. If it ends at a higher elevation, so let's say you're playing basketball, right? You're shooting, and you're shooting from below the hoop. In that case, you actually want to shoot a little more than 45 degrees, a little higher than 45 degrees. So when it gets to the same height as the hoop, it's at a 45-degree angle. And physicists have actually done research. If you're playing basketball, the angle that gives you the optimum range is also the angle that's going to give you the most forgiveness if you throw it too hard or too soft, or your angle is too steep or too flat. So the optimal angle is optimal for everything involved. Okay, going back to the slides, there's a little, I actually didn't start the presentation. Got to do the presentation to actually see this. This is a little simulator that allows us to play with the speed and the launch angle. Now, I'm not doing this mathematically, just playing around with numbers. So let's start by seeing what it does right now. Okay, he overshot. So if I want to make this motorcycle rider make it, what am I going to have to do? What two things can I change to make him not overshoot the pillows we're supposed to land on? Velocity. I can change velocity. Which way should I change the velocity?
A little less.
Okay, a little less. So let's just lower that speed a little. Okay, I'm going to lower it a little less. I went down 2 just so we can see. Okay, that was about the same amount, so going up to 7, which is halfway in between, might be a good guess. Right, I figure it's better to take a big cut. So 7 was just the minimum. Probably could increase it a fair amount and still make it, because he's got a range there. 7.3 is nice and comfortable. So that's one thing I could do, is change the velocity. Now let's get it back to the 8 that it started at. What's the second thing I could have done to shorten the distance he travels in the air? Change the angle. Which way should I change it? Either is the correct answer. It doesn't matter, because 45 degrees is the angle that's going to have him travel the farthest. So let's lower the angle. Let's say bring it down to 40 degrees. Well, close enough. 39.6. That did not shorten it enough. So let's go down some more. Bring it down to 35. Yeah, 35 is the raw minimum there, or maximum angle, I mean. Bring it down to 30 degrees. There we go. 30 degrees, nice and smooth, he lands on the target. Now let's try increasing the angle. So that went down 15. Let's try going up 15 to 60 degrees. Okay, 60 degrees landed in the same place. Now let's say you're Evel Knievel here. What angle would you want to do this at? Yeah, you'd rather do it at 30. Why is that? Yeah, it's not so jarring of a crash because you didn't go as high. So at the speed of 8 meters per second, 30 degrees gets you there, and you don't hit very hard. And of course, if I wanted to get my softest hit, I'll go ahead and crank. Well, I can't go an angle. Okay, there we go. Let's try my angle 20 degrees. 20 degrees, I still overshot, so I got to go a little higher. If I go maximum, actually, stay our flash angle, just slow her down a little bit. There. 20 degrees at 9.5 meters per second. I went faster, went flatter, but it's going to be easier to land. Now, if you are Robbie Knievel, or in my generation, it was his dad, Evel Knievel, you're trying to figure out how you're going to jump something big, like Evel Knievel. I'm going to jump the Snake River Canyon. You don't just say, I'm going to build me a ramp and I'll go as fast as I can and see what happens. That is not the way to live very long. You sit down. Let's be honest, the person who's riding the bike probably isn't smart enough to do all the calculations. If they're smart enough to do all the calculations, they'd have something more to live for, and they wouldn't be doing the stupid stuff. But they turn to their friend who loves to see them risk their life and say, okay, how fast do I need to go and what angle do I need to have to make this jump safely? And then that person's going to take into account the distance, the change in elevation, and what factor that we don't talk about here? The air. And so they're going to do some rather complicated calculations of what will be needed. And what do you think they're going to do after they do those calculations? Yeah. They what? Do them again. Well, yeah, do them again is a good choice. But then they're going to let's go get a football field. Let's make a ramp and get the height so they're the same. Now let's see if we land it right, We'll put a bunch of pads here so if it doesn't land right, we don't die, and make sure the calculations work. And of course, you still don't know when you do it because there's things you can't control. Like if you're jumping the Snake River Canyon, there could be air currents that are coming up that you didn't account for that will change the flight. And if you overshoot, that's almost as bad as undershooting. So, oh my goodness. I guess I waited too long, went to sleep. So that's an example. Now, there are some things I can do here. I can show vectors. So now I can do this. We see the vertical and horizontal. Those are the components of the rider's velocity. So he's going with a speed of 9.5 meters per second at this angle of 20 degrees elevation. So he has a horizontal component. Component means piece. The horizontal piece of his velocity is 8.92 meters per second. You get that number just using trigonometry. You take the 9.5 multiplied by cosine of this angle, 20 degrees, it gives you 8.92. His vertical is 3.24 meters per second. If I want to calculate how long he's in the air, I'll take the vertical component And I'll say, okay, so he starts with an upward speed of 3.24 meters per second. How fast do you think his vertical speed will be when he gets back to the same height he started from? I didn't actually talk about this yesterday. It was in one of the graphics, and I forgot to talk about it. Not yesterday. When you throw the ball up, go ahead. When you throw the ball up, as it goes up and comes down, the acceleration is constant. So its speed at any elevation is the same whether it's going up or down. It's just the direction that changes. So it's going up. If I throw it up when it gets to where my fingers are, let's say it's going 3 meters per second up. When it comes down, it's at that same elevation. It'll again be going 3 meters per second, just down. So the speeds are symmetric about the apex. Of course, the velocities are anti-symmetric because they're opposite directions. And that's because of the constant acceleration. So if he leaves the jump at a vertical speed of 3.24 meters per second, how fast will he be traveling when he hits the ground? He'll be at the same elevation, so he'll have a downward speed of 3.24 meters per second. So then I can just say, well, the change in speed, and I'm going to change this back over so I can do the calculation. So we just have the change in speed is equal to final speed minus the initial speed. Why is that a minus sign again? Right here, why is that a minus sign? Because he's going down. So that's the change in speed, and we know that change in speed is equal to acceleration multiplied by change in time. So that means the time he's in the air is just going to be that change in speed divided by the acceleration. 3.24 times 2 is 6.48. And what's the acceleration of gravity? It's 9.80 meters per second squared minus, because it's down. The minus is canceled, which is really good, because it's really unlikely that he's going to be in the air for a negative amount of time. And so we just take that and we divide the two. Right now it's not set up so you can see my math. Apparently it's not set up so I can pull over my math thing either. Well, 6.48 divided by 9.8 is about 2/3. So he's going to be in the air for about 2/3 of a second in this jump. Now if it's in the air for 2/3 of a second, let's say that delta t was equal to 2/3, just because I don't have a calculator that's working at the instant. Then I can calculate how far he travels, because in the horizontal direction, delta t. What was his acceleration in the horizontal direction? Zero, because the acceleration was only vertical. So this here was 0, and I just have, I know you don't remember the number anymore, but it was 8.92 meters per second was the horizontal component, times that 2/3 of a second. And so the distance is 2/3 of 8.92, which is somewhere around 6 meters. And so that's how we go through the calculations. The calculation, the equation that was given in that video clip comes by combining the work that I did with these two pieces. It's just taking the work we did and combining it into one equation. Now, for your work, like homework problems, test problems, you should be able to do problems like I did here. You're not going to be required to do the entire problem. You would have to do, one of the pieces, essentially. So, let me actually turn the light back on. You don't need that light off anymore. Whoops. Yeah, well, that works. Any questions on how I did this?
Is air always meant for
Is air always negligible? I'm glad you asked. I think that's my next slide. No, it's the one after this. But that's okay. We've already talked about everything on there. Not after that. After that, okay. We talked about those ideas. We got this clicker question, and then I will answer that question. Because it's, of course, a vital... Oh, goodness gracious. I don't know what's going on, but I will just go here and start. Okay, you can answer now. And since it didn't start on time, I will let you know. For the high school students, well, for everyone who's not a high school student, we have two guests who are here for college days. For the high school students, as part of what we do in the class, I have students answer questions to show their understanding. It's actually more to test themselves to see if they understand. So if they get it wrong, they can immediately say, ooh, what was I thinking wrong? If they get it right, they can feel good about it. So the truth is I don't know who answered what. We had 6 people that said the upper one will take more time, 1 person that said the lower one will take more time, and 3 people that said they're the same time. Now, the way to truly answer this question is really simple. The higher it goes, the longer it's going to be in the air. Right? Because you have the acceleration of gravity, that constant acceleration is downward. So if you make it go higher, you have to throw it harder and it has to travel a bigger distance. So which one of them goes higher? Clearly the upper one. So the correct answer was the one that the majority answered. The upper one is going to be in the air longer. Now, if this angle here is 45 degrees, in which one does the pitcher throw the ball harder? Which one does the ball have a higher speed? Okay, it needs to be actually the lower one with the higher speed because it's not going to be in the air as long, but it needs to cover the same distance. So the time is shorter and you have the same horizontal distance, so it has to have a higher speed. Now, if you threw it like this, that would also have to be faster. The slowest speed you can make it with is at the 45-degree angle. Okay, this better be the one. Okay, this is the one. Effects of air. Air makes a huge difference. So I put some links on here that talk about a lot of physics. But if you look at the top left picture, that top left picture is just illustrating what's going on. Now the colors here are not great, but you have the ball is spinning, and because that's spinning, you have reduced drag. That means the force of air resistance is actually smaller if the ball is spinning than if it's not. So air resistance isn't going to slow it down as much. But then you have another effect there, and that is the lift. Because the ball is spinning, okay, so you have me missing. Okay, there we go. It worked for one time. Okay, so here you have the ball is spinning. And that spinning, its backspin, results in a net force that is upward. And so that upward force is called lift because, hey, surprise, it's upward. And so the backspin on the ball makes it so it has a force that pushes it up. And so because it has a force pushing it up, it's going to go much higher than it would have without that spin. And so the actual flight goes higher. You know, here's the maximum you would have had if you didn't have spin on the ball or if there was no air. If you have the spin, it comes out and it hits its maximum height out here, somewhere just a little past where it would have hit the ground. Of course, then it comes down and you notice this is far from symmetric. The reason it's far from symmetric is because air resistance causes it to slow down. And so its horizontal speed doesn't stay constant because of that air resistance, making it so it plops down. Now, if you're a golfer, that's great. Because if it goes up like that and plops almost vertical, it's not going to roll much. So it'll be close to where you actually hit it and not go all over the place. Of course, if you put more spin on a ball, like you use a pitching wedge, you can make it draw back because it's still spinning when it hits the ground enough to pull it back toward you. And so that's often, for a short shot, you shoot past the hole and have it pull back toward you, depending on the slope of the green. None of this action would happen if there was no air. If there was no air, it would just go like we've been talking about. So air makes a huge difference here. And likewise, if you were to jump out of an airplane, air makes a huge difference. One of the funny things, when I was teaching at PHYS, I went skiing with the kids, and I was racing with some other kids. And I was just blowing Jason away. And I got down to the very bottom, and there was just this little roller that you always just go over, no big deal. But I was flying. And so I went flying like 50 feet, wiped out all nasty, had to climb back to get my skis. I just stomped in, and then Jason passed me. So I lost the race. Felt really bad. So the next year I'm all, hey, Huang, let's do it again. And we start racing. Of course, when you're skiing and racing, what are you doing? Yeah, you're tucked. You're not like, la, 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 la. You're down to tuck. Why are you doing that? Less air resistance. As we'll see in a few moments, that's a force that's pushing you back. So you get down that tuck to reduce your air resistance. And so I get down that tuck and I start booking. And I was suddenly scared because I'd had that big wipeout the previous year. And so I would, get booking, I'd pass him up, and I'd like stand up, oh, that's too fast for me. He starts catching up, and I'm like, oh, God. It was a terrible race. Anyone watching would have just laughed at me. Because, when you stand up, when you've been in a tuck and you stand up, you really feel it pushing you back because of the air resistance. So if you ever fall out of an airplane, don't make like a javelin. You want to do the spread eagle thing. There, at least I've read stories about people who have fallen out of airplanes from significant heights, like a mile up, and survived. Because, the terminal velocity is what we call it. There's a maximum speed you hit, and if you're all spread eagled and you're wearing loose, flappy clothes, it's somewhere around 50 miles an hour. And 50 miles an hour, if you hit the right surface, you could survive. Yeah. Yes. If you hit the wrong surface, you're going to break everything. If you hit a bunch of bushes, you might end up with sticks through your body, but you won't break everything. If you land on water or concrete, man, you're going to break everything. Okay, let's talk about forces. Force and mass and acceleration are the things that we're going to specifically focus on here. Now, force I've already kind of talked about, but here we get official. A force is anything that pushes or pulls. So if I come and I say, Christy has been a very naughty girl because she brought drink into my classroom. Sign outside says no food or drink. I picked it up. I pulled on it, right? I put a force on it. Anytime I push or pull on something, I'm putting a force on it. That's what it is. So that's an easy enough idea. If I step on a scale, I'm pushing down on the scale, right? That's the force I'm pushing on the scale. And the scale tells me some just really bad number of pounds. That scale is telling me how much force I'm pushing on it with. Now what do we call that? The weight. So the weight is just a measurement of the force that you push down on the ground with. So, some of us weigh more than others. You look at me and you could have guessed I weigh more than all of you. Why do I'm not asking to be ridiculed, but why can you look at me and know that I weigh more than the rest of you? More mass. I have more mass. Mass is a measurement of how much stuff is present. There is just more of me than there is the rest of you. Don't worry, you have time to catch up. When I was your age, actually, when I was a freshman, I was the same way as Ollie. I gained like 15 pounds every year in college because, you know, I'm eating buffet style in the cafeteria. Oh, I love that. Anyway, so mass is a measurement of how much of you there is. So I mentioned before, if you start here on Earth and you go to the moon, assuming you do it quickly, there's probably going to be just about as much of you when you get to the moon as there is when you leave the Earth. So which thing has stayed the same when you go from here to the moon? Your mass or your weight? Your mass, because the mass is the measurement of how much of you there is. Your weight is the force you're going to push down on the planet, or in that case, the moon with. Well, it turns out the acceleration of gravity on the moon is only 1/6 of what it is on Earth. You probably noticed in the videos from the moon that the hammer wasn't falling as fast as it would have on Earth, because the acceleration is only about 1/6. So your weight, it turns out, would also be only 1/6 on the moon. So you lose most of your weight, but didn't lose any mass. Which one do we really care about? The mass. Now, units are an important thing. We talked about measuring, and so the units of force have the name Newton, named after, of course, Sir Isaac Newton. Now, I just said when I step on a scale, it measures my weight in pounds, and pounds are a weight, a force. What's the difference? Newton is the international system, or System International, or something like that, unit for force. The pound, you can call it an imperial unit or an English unit. Of course, the English don't use English units, so it's better to say imperial, I suppose, of force. And we'll learn in just a little bit what makes up a Newton versus a pound. By the way, the abbreviation for Newtons is very simple. N. What's the abbreviation for pounds? LB for pound, or usually we see LBS for pounds. Anybody know what LB stands for? It's a sign of the zodiac. Libra. That's Libras. What is Libra doing in the picture for the sign of the zodiac? She's holding up the scales as a balance. That's where we get that from. So that LBS is actually Libras, which I always, as a kid, was really like, what in the world is an LBS? And what the PSI? I thought maybe a PSI and an LBS were the same thing. Of course, they're not. I now know. So we have force and mass. Weight is which of those two things? A force or mass? Which one is weight? Force. So this is a little redundant. Force, mass, and weight play critical roles, while weight is just a force. So kind of redundant. Where do we get our ideas from? I've already talked about Aristotle's idea. Aristotle said everything is made up of those four elements: earth, water, air, and fire. And, you know, things, weight, are just related to how much of those they have, and they have a natural position. They naturally want to be, if it's earth, it naturally wants to be down. If it's water, it naturally wants to be on top of the earth, and so on. Well, that was Aristotle's idea, and then Galileo Galilei, I just like saying both of his names, he was the person that said, no, I don't think there's a natural position, and I don't even think that how much stuff is present is all that important for what an object does. And so he did his experiment, and indeed he found that there is not a natural state for matter. Right? Aristotle's natural state is, if it's got earth, it's going to be down there at rest. And anything that makes it not do that is just an unnatural force, but in the end, if you remove the unnatural force, it'll end up there. Galileo said, no, it's just going to keep going. And then Sir Isaac Newton came up with 3 laws that clarify the situation for us. So, of course, we spent a lot of time focusing on Sir Isaac Newton because it clarifies the situation. So, another clicker question. If you push this chair across the room, and then you stop, and it doesn't hit the wall, is the chair going to stop when you stop pushing, or is it going to keep going? So, yes is it'll continue to move. No is it will stop. We're saying real life. Okay. Like you just go to your dorm room and you do this experiment. In this case, it's a hardwood floor. It doesn't really matter. Let's say it doesn't have wheels.
Are you saying that the chair is going to keep going until it hits the wall after you're done?
Yeah, is it going to keep going forever until it hits the wall, or is it going to stop eventually? Okay, we have answers from everyone. 1 person said it keeps going. 9 people said it stopped. Now, going back to ideas of some of the brightest minds in human history, Aristotle agrees with the 1. Right? Wrong. Aristotle agrees with the 9, that it will stop. And Galileo said the 1, except if you have something that pushes on it, it will still stop. See, Aristotle took the fact that we know it's going to stop. You push that chair, it's rubbing on the floor, you stop pushing, it's going to stop. And Aristotle said that's because its natural motion is to be stopped. And Galileo said, no, it's not because its natural motion is to be stopped. It's because it was sliding on the floor, and the floor was providing a force. It was pushing on it and brought it to a stop. So both of them, in the end, say, in this case, yes, it's going to stop. But the reason why is different. And so it's easier to understand how Aristotle said it had this natural motion, because that's what it does. Everything, I make this slide, flips over and stops. It stops. Aristotle says, well, that must be its natural thing. Galileo says, no, something had to stop it. So, throwing a baseball. I'm really going to hit Denver this time. You ready? There. Okay, so I throw the ball. Once it leaves my hand, I'm no longer touching it. I can't push on it anymore. And Aristotle understood that. He knew I wasn't continuing to push. There wasn't a continuation of my push once it left my hand. But he also knew that the ball didn't just stop and fall straight down. It kept going. And so he's like, well, if its natural thing is to stop, the only way it keeps going is if there's an unnatural force, if there's something pushing on it. And so Aristotle says, well, as it goes through the air parts and then comes behind it and pushes it. And so the air is keeping it going. Now we get to Sir Isaac Newton, and he's the one who put laws to this. So Galileo just said, no, it has the propensity to keep going. It has an inertia. Inertia is the term we use for something's propensity to keep going. And we can measure an object's inertia. We call it the mass. Mass is a measurement of inertia. It's a measurement of how much a thing has a propensity to keep moving at a constant velocity. But then Sir Isaac Newton gives us Newton's first law. Yes, remember I did that quote about him standing on the shoulders of his predecessors. And so he came up with, I do need to talk about this, but I want to talk about this first. The first law. The first law says that if the net force on an object is 0, then it will keep in constant motion. Constant motion means constant velocity. There I put the word uniform motion. It still means constant velocity. So now I'm standing here right here. am I in motion? Assuming the Earth is stationary, of course we make that approximation too, then I'm stationary. Am I in uniform motion if I'm stationary? Yes. So I have uniform motion. According to Newton's law, first law, if I'm in uniform motion, what does that tell you about the forces acting on me? They add up to zero. Keep in mind it's the net force. It's adding all the forces up. Are there any forces acting on me? The floor. The floor is pushing on me. It's pushing up to keep me from falling through the floor. That's what the preceding slide was. The force that's pushing out of the floor to keep me from falling through the floor, we call the normal force. So here's stick figure me, and I have a force that is pushing up. When we do problems, we put arrows. I can't draw upward. I can only do downward, apparently, to indicate the forces. So I have an upward force on me to keep me from falling through the floor, and we call it the normal force. The word normal is a math word that means coming out of a surface. So for this tabletop, the surface is horizontal. Normal is the direction coming directly out of that, so vertical is coming normal to this tabletop. If I go to the wall, now the surface is vertical. What direction would coming straight out of the wall be? See that, Rachel? Denford pointed, right? It's going to be horizontal this direction. So normal does not mean upward. It means directly out of the surface. So I have this normal force pushing up on me from the ground. If that was the only force acting on me, I wouldn't have uniform motion. I have to have another force. We haven't talked about it yet, but what is that other force? The what?
Gravity.
I still didn't hear.
Gravity.
Gravity, yes. What I thought I heard was hot air. I was like, no, that's what's coming out of my mouth. The force of gravity is pushing down on me. And so now I have these two forces, and I can say, well, by the very fact that I am in uniform motion, those two forces have to add up to zero. So I can add those together. Upward one I consider positive, the downward one I consider negative. Add them together, and they have to add up to zero. Now what if I start walking to the side? When I started walking, I wasn't in uniform motion. I was changing my motion. I was accelerating. So if I take this law for an object that is in constant motion has a net force of zero, it's not a truly logical statement, but it's true to reverse it. Right? It's flawed logic to try to reverse it. Anyone here in Origins class just talked about it on Wednesday? No. Okay. But the fact is still true. Since I was accelerating, since I was changing my motion, there had to be a force making me move sideways. What force made me move sideways? Which one?
Your leg.
Okay, my legs were involved. My legs pushed against the ground. And friction pushed back. And friction is what made me move. If I were to go out there and stand on some of the ice, and I did the same thing, what would happen? Yeah, my foot would just go out because there's no friction. I can push my leg just the same. But if I don't have friction to push back, I'm not going to start moving. Instead, my leg will just go out and I'll come down and land on my, whatever I land on, depending on my coordination. Once I start moving, if I'm moving at a constant velocity, is that uniform motion? Yes. So if I have constant velocity, uniform motion, what does that tell you about the net force? Back to zero. Yes, I have only 1 minute left. So let's get to Newton's second law. Hopefully this is Newton's second law. Newton's second law actually makes Newton's first law a moot point. Newton's first law is called the law of inertia because it defines what inertia is, that propensity to go in constant motion unless something acts on you. The second law gives us the equation that predicts the first law. The first law says the net force acting on something is inversely proportional to mass and acceleration. So you end up with the net force equals mass times acceleration. These two things are exactly the same. This symbol here, that's a capital Greek S, sigma. And we use the capital Greek S, sigma, to mean sum, right? Sum starts with S. And so this means the sum of all the forces. Net force means the sum of all the forces. So those mean the same thing. It's equal to the mass of the object multiplied by the acceleration of the object. I'm going to end with one thing here. What's the unit of mass? It's the kilogram. So the units here are going to be kilograms times acceleration. What are its units? Meters per second squared. Now I just realized we didn't say kilograms, I don't think, once today, but we did talk about kilograms in chapter 1 when we talked about units. So the force has units of kilogram meters per second squared. But what did I just say like 7 minutes ago that the units for force were? Newtons. So 1 Newton is 1 kilogram meter per second squared. If you were doing it in the imperial system, the unit of mass for the imperial system is the slug. And acceleration is feet per second squared. So for the imperial system, a slug times a foot per second squared is equal to a libra, a pound. And with that, we shall end our week. Have a swell weekend. Unfortunately, it's just the Pro Bowl. Nobody cares. But next week, Charles Woodson will be there for his last professional football game of his life.